Agora vamos ter a palestra do diretor executivo da Linux International, John Hall, Mad Dog, sobre performance de software e como não é só sobre velocidade. I'd like to thank him for coming all the way over here to Brazil and to invite him up here.
I hope that this is working. I think it's working too good. You in the back row, can you see this? Neither can I, because there's nothing there. But if you were in my class, I would make you sit up front. These computer things, they're amazing. I remember some of my first computers would fill this room. In fact, it would fill 2 of these rooms. Okay, I'm going to start. My talk tonight is entitled Software Performance. It is not all about speed. I know that that is going to distress some of you gaming people who spend a lot of money buying these computer systems that have 800 or 1,000 watt power supplies. But I started programming in 1969, and we were talking about kilowatts of electricity back then, not just tens of watts or thousands of watts. So who am I? For those of you that do not know me, I started off being an electrical engineer, starting at a university like this one, studying to be an electrical engineer. But I was almost electrocuted by 13,600 volts and 800 amps. So I decided to try out these new computer things because they seemed to be relatively safe. The worst thing that could happen to me was I would get a paper cut from a card or the printout. You don't use any of those anymore anyway. And I switched to become half business with a minor in computer science. Because you see, back in those days, you weren't a professional programmer. There was no such thing as a professional programmer. You were a physicist who needed to program. You were an electrical engineer who needed to program. You were a math student who needed to program. There was no computer science degree. And in 2 weeks, I'm going to be at the University of Sao Paulo, in Sao Paulo, to help celebrate the first computer science class that actually graduated from there 40 years ago. It makes me feel a little bit bad that I graduated before that. But I started programming, and I programmed on mainframes, IBM mainframes, in assembler language for 5 years. And then I got involved with Unix, and I've been doing Unix since 1980. I was a systems administrator at Bell Laboratories. And in May of 1994, I met Linus Torvalds. We'll get more into him a little bit later. So I've been using Linux since then. I worked for very large companies. Aetna Life and Casualty was the largest commercial user of IBM equipment in the free world. We didn't know what the Russians and the Chinese were doing. And the NSA was obviously using computers then. So we didn't know what they were doing. And we didn't want to know what they were doing. And, so it goes to show, if you put enough adjectives around something, you can be the best of anything. I am the most handsome guy with a white beard and white hair standing up on this stage. But Aetna was a very large company, and we programmed these machines in assembly language. And then I went on to places like Digital Equipment Corporation, where I spent 16 years bringing out operating systems. I've had a wide variety of jobs. This is good news to you, because after you've done some programming, if you sit there and you say, I really can't stand sitting there in my seat hour after hour, day after day, trying to solve these problems. There's a wide range of things you can do. And actually, you'll find out more about those tomorrow night. We might talk about how to make money with free software. So I've been a wide variety of things besides a programmer. I've been a technical marketing manager and a product manager and those things. But most importantly, I've taught compilers and operating system design. I taught for 3.5 years in a small technical college and then another 4 years in universities. But I've been, most importantly, the person waiting to get a bug fix or something from a vendor, and I've also been a vendor trying to get that bug fix to the customer. And again, tomorrow night you'll hear a little bit more about this. I like to think of myself as pragmatic, a person who believes in a philosophy but doesn't let it rule their life. Now, that's me in general, and my little clicker isn't working. Okay, I'm probably going to have to do this by hand. There we go. Now, as I said, in May of 1994, I met Linus Torvalds, and I saw Linux for the first time. Now, the company I worked for had this processor called the Alpha. It was a 64-bit processor, and it was the fastest microprocessor in the world. We actually went into the Guinness Book of Records as being the fastest microprocessor. Now, I make a big deal out of 32-bit versus 64-bit. With 32 bits, you can access 4 billion bytes of data. That sounds like a lot, doesn't it? It does, until you're making a movie like Lord of the Rings. Do the math. 70 millimeter film, 4,000 pixels per millimeter, 3 bytes in depth at least, and many thousands and thousands of frames. And these frames are not individual frames, they actually depend on each other. So it'd be very nice if you could bring all of that into the virtual memory of the computer at one time. If you're designing an airplane with a 32-bit computer, you might be able to design the cockpit. But with 64 bits, you could design the entire airplane and then do it again for every 6 months of the airplane's life. With 32 bits, you can store 4 billion bytes. But with 64 bits, you can store 4 billion times 4 billion bytes. That's enough to fill up a disk drive, a 1 gigabyte disk drive, every second of the day and night, every day of the year for the next 5,386 years. And still have space left over. And yes, I took into account leap year, and no leap year, and leap year. Or you can store 128 bytes of data for every square millimeter on the surface of the Earth, including all the oceans. It's a lot of data. And when I saw Linus and Linux, I said to him, would you like to port Linux to a 64-bit system? And oh, by the way, get the Intel-isms out of it. Now, this is no slight against Intel, okay? But the thing is, when you have a programmer and they're working on a particular architecture, programmers being what programmers are, they decide they're going to take advantage of the architecture to do quick things, quick hacks, okay? That's bad when you want your software to be portable. Because then when you take it to the next architecture, you have to go back and find all those little quick hacks and get rid of them. And there's lots of parts of the Linux kernel which should be portable. The scheduler should work the same on almost every machine. Upper level memory management should work the same on almost every machine. The I/O controlling scheduling should work the same on almost. It's the lower parts of these that are different. And I wanted him to be able to get the Intellisms out of the Linux kernel. So I gave him an alpha processor, and I got a team of engineers at Digital to go ahead and help with this port. Now there's another thing you should learn when you go into business. You will be told that what you have to do to get something going in your company is you write a proposal. And then you give it to your management, and they look at it, they think about it, they stroke their beards, and they see if they have money in the budget, and all those types of things. That's not the way you get something done. The way you get something done is the same way you do in politics. You pull in favors. And because I'd been in digital for 16 years, there was a lot of people who owed me favors. And I pulled them in. And so, in 1 year, we had the Alpha Linux port done by people who had never even met each other face to face. It was truly amazing. And I went on to become the executive director of Linux International, where I helped to do things like start up the Linux Standard Base Project, start up LPI, Linux Professional Institute, for certification of systems administrators, and I helped to defend the Linux trademark so that anybody could use it. And for the last 20 years, I've been going around the world to audiences like this to talk about free software and how you can make money or save money with it. But that's not why we're here tonight. I'm going to go away from that for tonight, because I'm going to talk about an organization known as Linero. Linero works with ARM chips. How many of you know what an ARM chip? How many don't know what an ARM chip is? Okay. How many of you know what a cell phone is? Good. Actually, Brazilians use more cell phones per person than any other country on the face of the earth. You know, you guys go around with like 2 cell phones, one in either ear. But most of those cell phones actually use a CPU of an architecture known as ARM, A-R-M. ARM that actually does not produce any of those chips. They only design them. And they license out the design to companies like Samsung, Hitachi, HTC, and others that you may have heard of. And they take those designs of the CPU, the GPU, and even other things like a field programmable gate array, and they put them into their hardware. Now, all of these companies would really like Linux to work well on them. And what they would do is they would hire 100 engineers to help work Linux, make all the changes and everything. And this was driving the Linux kernel engineers crazy, because they had all these companies trying to put code into the Linux kernel that did exactly the same thing. So a friend of mine created an organization called Linero. And he said, give us 2 of your engineers, and we're going to work together in a collaborative effort, just like the Linux kernel is developed. And we will then submit 1 group of patches to the Linux kernel instead of 100 doing the same thing. So they thought this was a good idea, and they created it. And about 6 months ago, they said ARM is coming out with a 64-bit chip. And they looked into the Linux kernel and to the Linux libraries, and they found out that there's 1,400 programs in GNU Linux that have assembly language in them. Now, those of you who have studied assembly language know it's not very portable. And this is creating a problem because they want these programs to work on the ARM64 chip. So they hired me because they said, Mad Dog, you did this once before. You got a community of people together to port something from 32 bits to 64. and we'd like the community to help us with this project. Now, porting is not very much fun. And I started to think about this, and I said, why don't we go through these pieces of code that were written a long time ago and see if we can actually make them work better. And we'll get more into that in a little bit as to what we're doing, how we're doing that. But we decided to change this from being a porting contest into a performance contest. Now, before I go on about the contest, we'll talk about why do we need performance. I had a friend of mine, his name was Leo, and he had a TV show, very good on computers. One day he made the mistake of saying to me, CPUs are fast enough. Really? I've been hearing this for like 30 years. Every year somebody, oh, isn't this fast? Oh, this is very great. This is fast enough. And then 2 years later, it goes into the trash. And then there's another faster computer, and then 2 years later, it goes in the trash. It's not because these computers weren't fast, it's because we keep coming up with bigger problems. We have more data to analyze. We have better analysis of the data. And this traditionally has been the way that we measure computer performance, that it's fast enough. Another comment I keep hearing is that Java is the only language that we need. We don't need to have assembly language. We don't need to have all these others. Java is the language. Let me tell you, folks, I will believe that the day that Larry Ellison, the president of Oracle, the owner of Java, rewrites the entire Oracle database in Java. I will believe it when the people in charge of a nuclear power plant rewrite the software that lowers the rods of the nuclear power plant to stop it from melting down. You know how fast the nuclear power plant melts down when it's melting? Very fast. So let's pretend I'm a processor and I'm in charge of the rods that are being lowered, and I'm running Java. Oh, it's getting really hot in here. I better lower the... Time for garbage collection. What was I doing again? Oh, wait a minute. What happened to everybody? No. Java is not for that. And people say, nobody codes in assembly language anymore. And I understand that, okay? I am not here to advocate that you code in assembly language. I did that for 7 years. I would wish it on nobody. But you need to know how the machine operates, because even in the world of Java, there are still registers in the CPU. There is still the interaction of the CPU with memory. In fact, now, levels of cache memory. And these are the things you need to know as you write your upper level code, because in the back of your mind, you should be thinking, this is what the compiler is going to generate. And it means all the difference in the world about your code working properly. Other people come along and say, virtual machines make all this obsolete because of the levels of abstraction. Doesn't that sound beautiful? And the answer is bullshit. And the reason why it's bullshit is because even in a virtual machine, if you're on the same architecture, it means that your instructions are actually hitting the hardware. Only when you do a privileged instruction does the virtual machine take over. So it's just as important. Now, if you're running on an emulator, that's different. But even emulators, you want them to be as efficient as possible. So let's take a look at what I talk about when I talk about performance. How many of you like programming games? I hate programming games. They really are of no interest to me whatsoever, okay? The last game I played was Hunt the Wumpus. That was probably about 1973. What I like to do is what I call real programming. And real programming starts with petabytes of data. Because I need to process that petabyte of data as quickly as possible. Maybe that petabyte of data is coming down from a satellite, and I get one chance to capture that data and to do the processing on it. That's it. I can't recreate that. I have to throw it away. Maybe I'm working with a cyclotron or something like, CERN, where they're generating so much data that they tried to store it, they couldn't possibly store it. They have to filter the data, throw away 99.999% of it, and they still store a petabyte of data a day. These are the types of things I get excited about. These are the types of problems I like to solve. I also like the very small, real-time stuff, the nuclear power plant. Now, I remember one time I had a conversation with Linus Torvalds. It was in the early days of Linux. And I said, Linus, the Linux kernel would have so much more application if we just had better soft real-time. He goes, what's the matter with the real-time in the Linux kernel? It's fine. I says, hey, Linus, how can you say that? He goes, well, when I'm playing Quake, the monster has a gun. I hit the button, I kill the monster. It's real time. I said, Linus, put a real gun in the monster's hand and see if you feel that way. Silence on the other end of the phone. A couple seconds later, he says, I see what you mean. In the next version of the Linux kernel, the real time was much better. And it's still getting better. And we're still getting closer to the time where you don't really need to dedicate an entire processor to only doing the real-time work, that you can take a chance of having a time-sharing system do your real-time type of work. Cell phone apps are another example of performance. Here we're not worried about how fast the thing is done, it's how efficiently is it done. And an illustration of efficiency is when I was talking with two cell phone manufacturers. They had some interleaved memory in the cell phone, and they said, isn't this great, because interleaving the memory means that the memory will be faster and the processor will do its work faster. But then another set of engineers said, no, that's horrible, because it means that we always have to have both banks of memory on all the time. If you separate the banks of memory, and this bank of memory is now free of data because the cell phone is quiet, it's not doing anything, then we can actually turn off this bank of memory and save electricity. This is the efficiency of the code, okay? And what you want, how you measure performance in a cell phone, is how long does your battery last? That's the measure of performance, right? Because you don't want to have to keep charging your battery every 15 minutes like you do with iOS. Now, if we're going to agree that cell phone batteries are very good to have, then we should take a look at server systems. Server systems and server farms like Google has. Because there, you're not being powered by a battery, but you are being powered by electricity, and they want to save as much electricity as possible. Now, when you can save electricity with CPUs, you actually win twice. Because not only do you have to power the CPU and the computer with your electricity, but you have to power your air conditioner to cool your system. The more electricity you save in powering your computer, the more electricity you save in powering your air conditioning. So these are the types of things that we want to do and think about with performance. And in addition to all of this, there are new architectures coming out, and really not really new. Field programmable gate arrays as a type of CPU have been around for a very long time. But they were very expensive to build, and they were very big. But with modern technology, we've gotten them down to be very small, very fast, and very powerful. But if you don't know how to program them, they're no use to you. Digital signal processing chips are the same way. Multi-core CPUs are the same way. You have to have your code efficient on them. And back in the days of Linux 1.0, when I first became involved with Linux, the kernel was a single-threaded kernel. It was not symmetrical multiprocessing. You didn't have a lot of the features that you have today, and the architectures of the CPUs were much simpler. You were lucky to have one CPU in a system, and the CPU was lucky to have one core. But today, even in your cell phones, you have CPUs that have 4 cores, 5 cores, 8 cores. And your server systems can have 64 cores or more. So maybe our software needs to be changed. Maybe the assembly language that's here in these modules needs to be ripped out because we can write it better with a compiler. So I'm going to show you, actually, the first computer I ever programmed was an IBM 1130. It was programmed in Fortran. Notice I just said Fortran. I didn't say Fortran 2, Fortran 4, Fortran 77, Fortran 90, high performance Fortran, or extended Fortran. Fortran. Capital letters, that's the way that Fortran is supposed to be spelled. And you only need one, Fortran, good for all time. And it had 4,000 words of memory, no operating system. When you wrote your program, you linked your device drivers into the program, and then you booted your program to run it in the computer. But the second computer I ever programmed was this one. That is a PDP-A computer. It had 4,000 12-bit words. That is an ASR 33 teletype. Notice there's no screen. It only works with paper. Paper is very expensive. Therefore, when you type something in, it doesn't appear on the paper. You remember it in memory. You're using something known as a dot editor. It has an invisible dot that goes around through your invisible file that you hold in your head. And every once in a while, you ask it to print out because the paper is really expensive. And it runs off of paper tape. This is the paper tape reader right here, and that's the paper tape punch. And it reads and writes paper tape at the rate of 5 bytes a second. Now, if your program is 3,000 characters long, yes, you're right, it takes about 5 minutes to print it out. That's what we did programming on. And I learned assembly language from a book, because there were no teachers of it. But nobody told me that assembly language was hard. And so I just did it. And what I learned was to write really great code, you needed to understand this machine language and the way the computer worked. Now, how I used that in my career was I was at Aetna Life and Casualty one day, and this COBOL programmer came up to me. COBOL is a business language, common business-oriented language. And it was kind of, Fortran was for scientific and COBOL was for business. And this person came up to me, it was a COBOL programmer, and said, I can't figure out what's wrong with my program. Could you help me? So I looked at their code, because I knew COBOL, and I said, I don't see anything wrong. I said, I think the compiler is making a mistake. The compiler made a mistake? I says, yes. The compiler is a program, just like your program. And just like your program, the compiler writer came in one day, hungover from the weekend, half asleep, wrote some code, didn't check it, put it into this pool, and boom! You had a compiler that makes mistakes. So we told the compiler to generate the assembly language and machine language for the IBM 360, and lo and behold, there was the mistake. Now the nice thing was that back in those days, most of these things were distributed in source code form, so we could actually go into the compiler and fix the problem. But if I did not know assembly language, we could have looked at the source code of that program forever and not figured it out. I had another program one time. My first job at Aetna was not to write new programs. My first job was to make other people's programs run faster. And my boss told me, if you can't make the program run at least twice as fast, don't bother with it. So I had this program that you put it on an IBM mainframe, and it would take like 15 hours to run. And not only did it run slowly, but as soon as you put it on the mainframe, every other program running on the mainframe slowed down. Every program on every computer, even remotely associated with that computer, slowed down. So my boss said, would you take a look at this and see what's wrong? And I ran it through a profiler, a program that shows you where the time is being spent in the program. And there was one machine language instruction that was taking up 99% of the wall clock time. So if the program ran in 100 minutes, 99 minutes were being spent on this one instruction. What is that instruction? Read the clock. That sounds like an innocent instruction, doesn't it? It's like feed your cat or something. It's warm and fuzzy inside. It's like looking at your watch. Read the clock. How difficult could this be? Except this instruction was used to create semaphores and locks inside of the kernel to coordinate symmetrical multiprocessing. That was its real purpose, not to tell you what the time of day was. And when this instruction was about to execute, or was executing, every single I/O operation on the computer had to come to a complete halt. All of the buffers of all of the I/Os had to be flushed into real memory. All of real memory, all of the cache of every CPU had to be flushed. All of the registers had to be put and quiesced. And then you read the clock. And then everything started back up again. And I looked at his program and I realized he was doing this 100,000 times during the course of his program. And I said, why are you doing this? He says, I want to find out what day it is. Couldn't you do that at the beginning of your program and store it in a variable? Because your program is not going to run for multiple days. You're really not. Oh yeah, I could do that. And the next night when his program ran, it went through so quickly that the operators thought it had crashed. And of course, no other computer slowed down. But here's the problem. He knew enough assembly language to be dangerous. And that's another problem. How many of you know what ASCII is? Or don't know how many of you don't know what ASCII is? Good. You must be computer science majors. There was another code called EBCDIC. And this was what IBM used instead of ASCII because IBM knew better. But ASCII went out because everybody else knew better too. And when you try to store a number for an index into an array, you should store it as a binary number, because the binary number is what the computer is going to use as the offset into the array. My friend who wrote this program didn't know that. He stored it in COBOL as what we call a picture 9 field. It's held as an epsidic number. And to convert the epsidic number to a packed decimal number and a packed decimal number to binary are the two slowest operations in the IBM instruction set, besides read the clock. And so every time he went to access his array, he had to do these conversions. He accessed the array, he added 1 to it, and then he converted it back and stored it. All he had to do was stick one tiny little word at the end of his declaration, comp, and it would have stored it as a binary number, and he would have eliminated millions of conversions every time his program ran. This is what happens when you don't understand what's going on. A friend of mine, David Mossberger Tang, wanted to multiply 2 very large arrays. Now remember, I started this by telling you what I think is real programming, petabytes of data. David feels the same way I do. Each of his arrays was a petabyte in size. And if you multiply 2 arrays of that size, the way you normally do when you learn algebra, you go row, 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 picking up your various pieces of data. But when you do the multiplication, you go column, 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 column down the other array. This is fine. You're staying in the cache of the CPU. This means you're doing a cache miss every time you pick up that piece of data. If, on the other hand, you invert the second array, now it's row, 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 row. You do your multiplication, you invert the answer, and you get exactly the same result, except it happens in 1/40th of the time. This is the type of thing you need to know. I'm not going to go into a great in-depth discussion about how I did this, but I took a program one time that ran on a PDP 1170, and it did a bubble sort. It was a bubble sort that did everything wrong. I mean, if there was a classic bubble sort that should be put into Knuth's book about sorting and searching, it would have been this one. To sort 1,206 records, each record was 32 bytes apiece. It took 10.5 hours on this computer. I could have punched all the numbers on the cards, thrown them up into the air, and picked them up off the floor in order, faster. And so I took a student of mine aside, and I said, we're going to rewrite this, but instead, we're going to do it in such a way that all the data tends to stay in memory. And we did, and the sort now took 3 minutes. The student made the unfortunate mistake of putting this onto his resume, his CV. Nobody believed that this could happen, but it did. So these are the things, again, you need to know the architecture, you need to know how the system is running. Now today, what's happening is a lot of high school students and some college students are learning Java, and they're learning Microsoft Office and Oracle instead of Office systems and databases. Now, I have no problem with people who want to learn networking to study Cisco as an example of networking. I have no problem with people studying Microsoft Office as an example of how to use an office system to make your business work better. But what you should be learning is the underlying principles of this. Because otherwise, In 5 years, when Microsoft comes out with the next version of Microsoft Office, I'm going to come to you and I'm going to ask for your diploma back. Because you learned Microsoft Office version 3.0. It's now Microsoft Office 4.0. You need to either come in for a refresher course or give me your diploma back. But if you learn the underlying principles, you can apply that for the rest of your life. And a lot of high school students these days get a computer system. They don't open it up. They don't see what's inside, because if they do, they void the warranty on their computer. They put a game on it. They package it as a game, and they never know how it works. Back in 1977, we had computers like the Commodore and the Amiga, and we would have to take programs in source code off the internet from bulletin boards, and we would type that in. We would see things like syntax error. We would see things like buffer overflow, and we had to figure out what those were. But the high school students of today don't typically have to do that, and so they see computers like this. Ooh, my friendly little computer. It runs my games. It's so nice. But in reality, computers look like this. And it isn't friendly. It hates everybody equally. And so the real life effects of this, as found out by the University of Cambridge, who developed the Raspberry Pi, was that the students coming in today knew less about computers than the students of 20 years ago. And so they decided that they were going to do something about this. A friend of mine who had a consulting company told me about somebody that they were interviewing for a job as a programmer, and when the guy mentioned something about cache, the interviewee said, "Oh yeah, that makes a computer run faster somehow. I don't really know anything about it. This is a terrifying problem." And so we have the Raspberry Pi, 35 US dollars, except in Brazil. I'm sorry, gang. Your tax system is terrible. But it's a nice little computer system. I think this is a nice little computer system for elementary school children, grades 1 to 6, because it has some problems. It's only a single core CPU. It only has half a gigabyte of memory, and there's nothing really interesting on it. Now, a more interesting computer is the Banana Pi. It has a dual-core ARM processor, so you can actually program and come up with race conditions in your parallel programming. It has a gigabyte of memory, and it has a SATA controller on board, so you can actually practice changing the code around the controller to see how much faster your I/O can be. And you can actually build a very nice little Beowulf supercomputer out of 5 of these to practice your programming of supercomputers. It costs $50 USD from China, and $50 USD should be able to slide right underneath of your customs people. So you can order this directly from China. They pay the freight. You can actually get it cheaper than you can get a Raspberry Pi here in Brazil. But this is just a couple of all these little computer systems. And the interesting thing about most of these, not the Galileo, that has an Intel chip on them, but every single one of those are an ARM chip. And they all have different things that they do very nicely. For example, this one over here has 2 ARM chips on it. Each one of them is 4 cores. And one of them has 4 cores that runs at a very low clock rate, but uses a very small amount of power. And the other runs at a faster clock rate and uses more electrical power. But you can turn it off. And so you run your operating system mostly on the slower one, but when you have some work to do, you make it go over and use the faster one until that's done, and then you go back. We call this the little big philosophy of running server systems. But the one I really wanted to talk tonight is the one I call the university student's Raspberry Pi. This is one that has a 2-core ARM processor in a system on a chip. It also has a field programmable gate array. Now, for those of you who don't know what a field programmable gate array is, I'm going to give a little mini lesson here. When you're programming a chip like an Intel chip or an ARM chip, they have a certain instruction set which is built by the transistors, built by the gates, being in a particular formation that they then accept your program as data and they process it. And then they also process regular data along with that. A field programmable gate array allows you to change the gates and put them into a certain order, so in effect you're writing your own instruction set. And then you feed the data through, and it actually processes the data much, much faster than your regular CPU. But it typically only does a very small program. So what type of small programs does it do? Encryption of a lot of data, decryption of a lot of data, video types of processing of data. All these types of things can be done with a field programmable gate array. Bitcoin mining. This is the world's cheapest, fastest, most power efficient Bitcoin mining computer in the world. We won't go into that. You'll hear more about Bitcoin mining in another talk, I think. It also has some digital signal processing chips, but then most interestingly, over here, this little chip right here is either a 16-core or a 64-core CPU that each core has a megabyte of main memory associated only with that core. And into that megabyte of memory, you put your instructions and your data, and then all 16 or 64 cores can process in parallel that data at one time. Hooking these two chips together is a mesh network that can transfer data between them at the rate of 1 gigabyte per second. This whole board uses 5 watts of electrical power, and it costs $125. Now, if you got this system, you could practice parallel programming, either on the 2-core ARM or on the multi-core CPU. You could practice programming a field programmable gate array, practice programming digital signal processing chips, and it's a very interesting board to program. So these are types of new processors that are available to us that we could take advantage of if we had people who knew how to program them. Now, when I started getting involved with GNU Linux, it was May of 1994. Version 1.0 of the kernel had just come out. However, a lot of the programs of GNU Linux had actually been written before that. The GNU system started up in 1984, 10 years before that. And actually, those GNU programs were modeled after stuff that happened with Unix that started in 1969. Okay? So a lot of the architecture of these came from the time when memory was $128,000 a megabyte, when CPUs cost $2.5 million, when memory did not have any cache to it because the cache was too expensive, when the GNU compilers were not as good at optimization as they are today. when algorithms weren't as well understood. And so now, that was why people wrote this assembly language that went into these programs, because they needed to have the speed that the compilers could not give them. And it was simple enough to write that assembly language because the architecture of the machine was simple. But today it's different. And memory costs a lot, is $10 a gigabyte or less. CPUs are multi-core. And the algorithms are better, and the GNU compilers are now almost, if not better, than commercial compilers. And you can get them for free. So with that, we're having a contest to take these 1,400 GNU Linux modules and make them better. To go over the code, to try new algorithms, to get them to run more efficiently, maybe in less memory if you're going into an embedded system, or maybe to take advantage of a 64-bit address space if you're running on a server. We want to be able to measure that performance and optimize the code at the same time porting it to ARM64. And if you document the performance increase and submit it to the website, you could win a contest, win the contest. So the goals of the contest are to make sure that all of the modules actually work on ARM64, and as much as possible, completely eliminate the assembly language that's in there. Some assembly language that's been in there for 35 years. Get rid of it. And that way we never have to worry about it again. The next architecture that comes along, we change the compilers and we can recompile the code, and it works. We also want to use this time to create a university course in performance, so that as we have people talking about different algorithms, different ways of making things better, that we can put all of this into a course and make the materials freely available to universities so that professors can take the materials and teach courses in performance programming. Now, when I talk about performance, again, it's not always just about the percentage of speed up of the application. We're going to have different categories to look at memory utilization, to look at things like cache utilization, battery life, electrical utilization, things like that. And we may also invent new intrinsics to go into the compilers to do specific things. We noticed as we were going through this code, there was a lot of assembly language that was doing the same thing over and over again. Why not build that into the compiler and get rid of the assembly language? So we could do that. And there may be other categories of performance improvement we haven't thought of, and we'd be happy to extend the contest for those. Now, what type of prizes would you get for this? Just by going onto the site and signing up and picking one module and testing it to see if it will port to ARM64, you'll get a very nice Linero t-shirt, golf shirt actually. And you'll be put into a pool to be drawn out for another prize, which we'll talk about in a second. If you do several of these ports, then we may give you credit to getting a free ARM development system. One of these little boards like this, like a banana pie, or maybe a parallella. And if you do like 10 or 15 ports, you might get one of these absolutely for free. And you'll be put into this pool for this larger prize. The larger prize is going to a Connect meeting. Next week, I will leave Brazil, I'll go back to the United States, and the week after that, I go to California to this thing called Connect. It's when all the engineers that belong to the Linero community come together in one place to do things like programming sprints, to talk about projects, to meet face to face. We hold these twice a year, and we alternate. Every year there's one in the United States, but we alternate between Europe and Asia. About 6 months ago, I was in Macau, China. Oddly enough, they speak Portuguese there. I couldn't understand them any better than I could understand you. But it was a great time, and we stayed at a great hotel with great food, and you got to talk with all the engineers who were there and exchange ideas. So every Connect meeting will be reaching into this pool of people, pulling out a name, and that person will be going to Connect. That's the porting side of the contest. There's also the performance side, which we'll get to in a moment. Now, what are the side effects of all of this? Even if you didn't win, you'll get the t-shirt, you may get one of the boards, but even if you didn't do that, what else do you get from this? You learn a really cool assembly language. And you're going to, because the ARM is a very nice assembly language, and you'll learn this so that you know how to do the port. You'll also learn code analysis techniques that you may not even know about. There's all sorts of tools for analyzing your programs, and we're going to be publishing these on the websites and showing you how to use them. You'll learn how to create better code overall so that you improve your own code. The best way of learning how to write good code is to look at other code that good coders wrote. And you'll build an open source portfolio. What does this mean? It means that if you participate in this contest and you take the code that you ported or you got better performance, you put it into a little book, you take and show it to somebody who wants to hire you as a programmer. This is what I did. Because it's open source, they could also look at the mailing lists of the project and see how you interacted with people. You can get letters of recommendation from the people in the project. Let's say you made the program run 10% faster. That's a big thing. And this is the type of thing that your employer would like to know that you can do. As I said, we want to create a university level course in optimization on this. And we'd also like to do some research into new optimization techniques. So this could be a research project for universities. We're looking for mentors, college professors and engineers who would like to mentor young students in doing this. And when we're asking for input for the porting side, we might ask simple questions like, what group of compilers or tool chain did you use? And what tests did you perform to make sure that the work you did was actually correct? You're also going to have to get this code to be accepted by the upstream maintainers of the code, because they're the ones who will have to be maintaining this long after you're gone. Now, for the performance side, we're going to ask a little bit more information. We're going to ask you to test the performance of the code before you did the work and the performance of the code after you did the work. And then we're going to take that performance improvement, and that will be the measure of who wins the performance side of the contest. The resources we have, we're going to have a list of different books that could help you. And a lot of times, the performance improvement may not even come from the code itself. It may come from the make file that's telling the compiler what to do. Because I remember when GCC only had 3 switches. No optimization, level 1 optimization, level 2 optimization. That was it. Today, you go to GCC, and there's like 147 different switches. And you can pick the one that might give you much better performance. So we're going to be putting more and more ideas, performance of resources up there for you to look at. The time frame for the contest is immediately. We have formalized the program. We put all the rules and everything up on the website. We're creating examples of how to do this work. That will be done next week at Connect. We're going to publish those on the website. Richard Henderson, who is in charge of the GNU C compiler for 64-bit machines, is coming to Connect, and he's going to be doing some of these examples for us. And by the end of 2014, we'll be picking some of the first people to go in these Connect meetings. And we're also looking for universities, doesn't have to be just one, will be a home for this, because this is a contest that is going to go on for perpetuity. You can always make code be better. So what should you do right now? Go and register at the site, read the information about the contest, select a module you want to work on. If you're interested in music, maybe it's one of the music-oriented modules. If you're interested in video, maybe it's one of the video-oriented modules. If you're interested in libraries design, could be that. One more story before I end. It was with the Alpha Linux port. Digital Equipment Corporation had a math library, the C math library, that we had done a lot of work on. We had hired a mathematician to help us make our math library the fastest in the world. When we started the Linux port, my company said, we'll give you a binary copy of the math library. But they refused to make the source code available. And of course, the free software world wanted the source code. They said, if we make the source code available, then Sun Microsystems might be able to take advantage of this, or IBM could take advantage of this. And I was the one who was being beaten up. And one day, they were beating me up, and I said, look, you guys think you're such great programmers. I challenge you to make a better math library. And there was silence on the internet. 3 days later, a message came across. The sine routine is 5% faster. 2 days later, cosine is 3% faster. 2 days after that, tangent, and subroutine by subroutine in the math library, the free software movement made a better math library than digital equipment corporations. And of course, the source code was available. So performance can be improved. Sometimes it's only 2 to 3%. But those of you who have worked with queuing theory know that 2 to 3% can mean a lot when you're trying to keep your nuclear power plant from melting. And with that, I'll take questions, comments, or ideas. There's my email address to send any type of things. There is the site for the contest. I want to take one quick little bit more message. Oops. Tomorrow night, I'm going to be giving a talk on how to make money with free software. And I want all of you to come to that and bring along your friends, even people who use Microsoft. And even people who use Apple. And I will tell you how to make how to make money with free software and with a program which we call Project Kawa. Thank you very much for coming. Do we have some time for some questions or something?
Anyone?
Oh, way up there. See, if you sat down here in the front, it would have been easy for him. Poor guy, he's been running around. Okay.
Sorry. Thank you for coming here. It's a great pleasure to have you here. I want to hear about. I want to hear you about what's that with how many switches we can put in GCC, we can put inside Linux kernel, and get some millions and millions and millions of source code lines. What to do with that? After all that performance, you can switch in. You can switch 1, switch 2, switch 3, switch for performance and performance and performance. But what for it? What to do with all that performance? I'm following the community behind OpenBSD, and their philosophy is very, very nice. Why so much switch to put in the market or whatever? Why put so many suites when who needs these suites are some not so many people.
I think I have the question. Who really
sorry, my English is not that good.
No, it's not that. As I explained to you, I work on very large problems. So, a year or two after I got involved with Linux, I went down to Auckland, New Zealand, and there was a physics professor down there who was working on a problem that one iteration of his problem took 10 weeks on a Spark computer system. And so every 10 weeks he would get one answer that he could then put back into his problem, run it through again for another iteration of 10 weeks. Unfortunately, what was happening at that time was that on the average of every 3 weeks, Auckland was having a power failure. And so he would start running his program, and it would run for sometimes 3 weeks, sometimes 4 weeks, but then on the 5th week there'd be a power failure, and he'd have to start all over again. So we took him an alpha processor that was much faster than the one he had, and it lowered the amount of time it took for him to do one iteration to 3 weeks. So on the average, he might be able to get 1 or 2 iterations. He hadn't gotten all the way through his program in over a year. Now, this could have been solved a different way. And as I was leaving, I said to him, why didn't you use checkpoint restart in your program? And being a physics professor first and a programmer second, he turned to me and said, what's checkpoint restart? And as I explained it to him, his face kind of fell because he realized if he had implemented that, he could have gotten his iterations even with the power failures. I didn't mention uninterruptible power supplies to him because that would have killed him. But it's this type of thing. The world's largest supercomputer has 800,000 cores in a number of systems that, again, would fill this room. If we could make the code 10% faster, they could save 80,000 cores and the electricity to run it and cool it. That's why we need to have the performance, and that's why we need the switches on GCC to tell it to do optimization for the Intel 386 or the Intel 486 or the Intel 586. It's why Arch Linux exists at all. That's why we need the options.
Once again, thank you very much for coming. You said you want to remove some assembly code from the code to make it more portable. But sometimes, isn't it better to leave an assembly to make it faster?
Okay, you have to take a look at why the assembly language code was put in there in the first place. It may have, in the early days of the GNU compilers, on the most part, they were about 30% slower. They generated code that was 30% slower than other commercial compilers that did very good optimization. So if you wanted to use GCC to run your program, it was very highly susceptible to slowdowns at places that were critical. However, today, GCC is as good as most commercial compilers. So you say, well, can GCC generate code today that is actually as fast as the assembly language code that you've put in there? And what's happening is that assembly language code is blocking that program from using other facilities, such as multi-threading, because the assembly language code was written for a single core processor. And if you run it on a processor that has multi-cores, it's going to block until you have only one core following that assembly language instruction. By allowing the compiler to go in and do that instead of the assembly language, you may get a speed up by allowing it to use multiple cores, as an example. And I'm not even talking about things like cache utilization and stuff like that the average programmer can't really keep in their mind. There will be places that you should leave the assembly language in, but those should be like 5 or 10 modules out of all this. None of these modules are anything in the kernel. The kernel engineers are going to take care of everything in the kernel that has to be done. But these are things in libraries. These are things in programs where at one time somebody thought they needed assembly language, and now what's happening is every new architecture that comes along, we have to do this work all over again. Now, the contest also specifically says that you can't do anything which is going to slow down the performance of the module on any architecture. So even though this is being sponsored by ARM and Linero, we will not tolerate a change to the module that's going to make it run slower on Intel than it does today. And I believe that most of the performance improvements we're actually going to get in a portable fashion that will go across architectures, so that the GNU Linux will run faster or better battery on every architecture. And remember that portions of Linux are also used in Android. So the types of work we're doing with the compilers and things like that will also help on Android phones. Some of the programs that we're changing may go into BSD, and therefore BSD will pick up. And I'd be happy to sponsor BSD code on this type of thing too, because the idea is to get better performing code, not just better performing ARM code. Of course, better performing ARM code goes over well too. Next question. Well, if you have any more questions, I'll be around for the next couple of days, and I'll be around for the next couple of days. So thank you very much.
Thank you. Queria agradecer mais uma vez ao Medog. Thank you very much for coming. It's been a great honor for Syncomp and for all of us.
I would also like to say that since you're all here, that this has been a very, very nice experience for me. I've enjoyed coming to university. I've enjoyed interacting and talking with you. And I think the guys who put on this and ladies who put on this contest or this conference have done a very, very good job. And I think that all of us owe them a round of applause. Thank you.